Well, good morning. Is it good? Yes, it's good. So, congratulations. We are crossing the equator. 3 weeks behind, 3 weeks ahead. We had a notion of a difference between a task and a problem. And just to review, when one has a goal and knows how to achieve it, that's a task. When one has a goal and doesn't know how to achieve it and has to create the solution, that's a problem. And there are many courses which call themselves science courses, but not all of them represent a scientific way of thinking. This does, and today we will have one more example of that. Starting from a question. A very common situation. All we have in this situation is a conductive loop and a bar magnet. We need to use definition of magnetic flux. For that, we need to know how magnetic field lines of a bar magnet look like. We have to draw those lines, and then we have to look at those lines at the location of the loop, and then we have to apply the definition of the flux, and then we have to choose the answer. So, oops, something like this. That's it. This is not an actual bar magnet. I couldn't lift it. It would be heavy. But in science, we always use models, which helps us to get rid of all unnecessary features and keep only necessary features of the phenomenon. So magnetic field lines are lines. For example, a single line might look like this. Those are loops, but it's a directional line. It has a direction. So that's what you should know. And for that, we have a mnemonic rule. The north is cold. No one wants to live there. Everybody leaves the north. That's it. So this tells us that's supposed to be the direction of this line. And what is a connection between a line and a magnetic field vector? Well, magnetic field vector cannot be bent. It's an arrow tangent to the line at any location where we measure it. For example, this will be the magnetic field vector at point P. A correct arrow, but not needed at all, because we need to look at the arrows at the location of the loop. That's what you have to draw. At least one arrow which represent the magnetic field vector at the location of the loop. So, not here, not here, not here, somewhere here. This is when I always wish I would have a third hand. Because we need a vector. A vector is an arrow not the area vector. We don't care about this, right? Why? Because there is no information about that. So if we go along a line, here we could draw a vector. Then we would have to apply a definition of a magnetic flux. No, magnetic field strength is not zero. The area of this loop is not zero. So now we have to say something about this letter. It represents something very specific. What does it represent? Between what and what?
The angle between B and A.
B and A. Exactly. And what do we know about A? And when the direction of electric current is known, we use the right-hand rule. Do we know the direction of electric current? No. Maybe it counterclockwise, maybe it is clockwise. So that's the answer. We don't know. Could have been positive, could have been negative. And of course, it's just a review of the rule. Yeah. When we know, we use. When we don't know, well, it's up to us. And this is a review of a definition of magnetic flux again. And we didn't tell about it last time, but if we multiply the units, yeah, Tesla times meter squared, that's going to be a unit of magnetic flux. But it has a special name, special symbol. Unfortunately, it has many different pronunciations. Weber, Weber, Weber. Choose yours. As long as you know it's WB, yeah, that's flux in international system of units. Now we are given the direction of the area vector. It is set for us to the left. So now, please tell me the magnetic flux at the location of this loop generated by this magnet is and basically you have to go back to question 2, add one more feature. Now you can see two directions, two arrows. You can see an angle between those directions. And that angle tells you something very specific because, again, B represents the strength, that's magnitude, never negative. A represents the area, positive number. So the value of the flux depends on the value of this cosine, and the value of the cosine depends on the value of this angle. And if we look at the pictures again, well, I just, oops, let's make it blue. I just look at the same magnet, which generates the same magnetic field. Well, this is another possible line, and this is our loop here. So, magnetic field. Area vector. That's the angle. So cosine of this angle it's a number, could be positive 0 or negative. So you choose one. What do you choose? Negative. It is negative. You can pick any number greater than 90. Definitely the angle is greater than 90 degrees. Calculate cosine of 180, 170, 160. So and that will give the flux to be negative. Well, this is our original experiment. Yeah? Remember the uniform magnetic field, non-uniform magnetic field, the loop. Do we have a loop? Yeah. And when the loop was traveling down, when it was, well, this is basically actually, so if we imagine that these lines point up, this is like magnetic field close to the North Pole. That's how lines go and go back to the south. And we move a loop closer to the magnet. So when it's far away, of course, magnetic field is weak and the flux is low. And when it's getting closer and closer, the flux increases. And we demonstrate this fact using two pictures. Well, but when we draw those pictures, we make a very specific assumption that we are looking from above, because that's what we see. Another person could have been looking from below, and these pictures would have different direction for the magnetic field relative to that person. So every time when we draw a magnetic field in a loop, through the loop, we assume a certain point of view. And here, when the loop is far away from the magnet, or the loop is in the region with the low flux, we can represent this picture, then more flux, and our analysis, how electrons would move, tells us that electric current in this situation would travel, and we say clockwise relative to that person. So that's a fact. We will be using this several times. And we saw an experiment. You can see it again with a slightly different modification. Classical experiment for a changing magnetic flux inducing electric current. See? Oops, stuck. Too much friction. We can see that the number of loops, of course, affects the current, even if I have the same magnet and move it with the same speed. Each individual loop generates its own electric current, so when we have more and more loops, stronger current travels in this coil. And first we can make a, well, logical transition. What's going to happen if we make a single change? What can we change? Well, we can change the direction of magnetic field. Instead of having a north pole up, we could have a south pole. What else could we change? We could change the velocity of this loop. Instead of approaching the magnet, it could move away from the magnet. That would affect magnetic flux. And naturally, we assume that a single change in the experiment would change the direction of this current. If instead of magnetic field traveling out of the screen, the magnetic field would have been traveling into the screen, electric current would be directed counterclockwise. So in general, we expect just 4 possible situations to happen, just 4 of them. This is our original analysis, but what if instead of increase in flux with the same direction of magnetic field, we would observe decrease in flux? What would it mean? Well, we don't change the orientation of the magnet, but instead of approaching the loop, the magnet, the loop would be moving away. So strong flux, weak flux. Now what else? Well, same. We flip the direction. If we change the direction, but the flux increases, the top picture, so the induced current points opposite to our original. But if we make another change, now also instead of increase in flux, we would observe a decrease in flux. The induced current would flip again. 2 flips would make it the same as before. And well, we do remember from last week that electric current also generates magnetic field, its own magnetic field. So the sequence is actually longer, more complicated than we thought. For when magnetic flux changes, it induces electric current, but that electric current in turn induces its own magnetic field, which of course has a name, the induced magnetic field. So now we have a combination of 2 magnetic fields, the external magnetic field and then the induced magnetic field, which is induced by the changing flux of the external magnetic field. So we know, again, when electric current travels counterclockwise, it induces magnetic field inside, out of the screen. When magnetic field in opposite direction, the induced magnetic field is into the screen. That's what we know, right? So now we're adding, first of all, this fact to the list of facts. That was number 1 for the motional EMF. That was number 2, that the loop starts acting like a circuit with the battery. And now, number 3, it also has its own magnetic field induced in it. So this is the Faraday's discovery in full. We have a loop, magnetic field changes, it induces electric current, that electric current induces a magnetic field, and of course everything has to be related and connected in some ways. Well, first, the same slide, the same information with symbolic representation. The external magnetic field has a flux, a certain location. If that flux changes, if the change of the flux is not 0, well, first of all, it induces electric field, which induces EMF, which induces electric current, which is related to EMF by the Ohm's law. But that electric current also induces an additional magnetic field. And all experiments prove this again and again. So, this is the Faraday's law. He established it, he proved it, that the magnitude of the EMF induced by the change of the external magnetic flux in a single loop is just equal to the rate of change of the flux. If the flux doesn't change, no EMF is induced, no EMF is induced, no electric current, nothing. But if the flux changes, no matter if it increases or decreases, it induces EMF with this magnitude. Rate of change, we could call it speed of change. Yeah? So EMF, the induced EMF, is just equal to the speed of the change of the flux. But the question is, if we want to calculate the actual value, we should make a choice between a plus or a minus. And that's not obvious at all. So First question. Well, first a question, which is the fourth question. Equation number 4. In our original experiment, electric current was induced clockwise. What does it say us about the direction of the induced magnetic field? Only 2 options to choose from. I would write more, but no space left. So make your choice, enter your answer. That is equation number 4. Just 20 minutes, and we're already. Who answered 5? You know I can find it out. So, number 2 is the most popular answer, and well, why would it not be? It's right here. Clockwise into the screen. According to the rule, of course. So this again is nothing new so far, just a review. And that's the answer. Now, the summary. That was the first fact. Now the second fact. And another summary. It's important to remember that most commonly we use this rule in order to figure out the direction of the induced magnetic field, or just magnetic field, if we know the direction of electric current. But the same rule also tells us what should be the direction of current if we know the direction of the field, because the same rule works both ways. It's the same picture, you just read it backwards. If magnetic field points into the screen, that means electric current which generates it should be clockwise. If magnetic field points out of the screen, that means electric current which generates it should point counterclockwise. So the same relationship, but we should use it differently. Now, we already saw 4 different situations for induced electric current. Now, of course, we can make a next step, a next transition. We only have 4 different situations for inducing magnetic field. We just have to add that symbol. If electric current is counterclockwise, induced magnetic field points out of the screen. If electric current is clockwise, the induced magnetic field points into the screen. Nothing new, basically, right? Now, this is a very important statement. Our original experiment, well, technically it was thought experiment, was based on a fact that a conductive coil was moving in a magnetic field, and that creates a force acting on the electrons, and as a result, we observe that electric current is induced, well, because EMF is induced. See? If you look. But nature has a symmetry. So from the point of view of the nature, it doesn't matter what is moving. So we can have a steady coil, but move a magnet. And we should observe exactly the same phenomenon. But the reason will be different. When the coil is moving, we can explain everything by a force acting from magnetic field on a charge traveling in magnetic field. But now, when magnet is moving, the charges, all electrons are at rest. So we cannot explain this phenomenon by applying the Lorenz's force anymore. Well, Faraday said, and he was right, and then Maxwell used it to derive his equations, that it doesn't matter what's moving. When we have changing magnetic flux at any location, there is electric field which is generated by that change. And in this situation, right here at this location, magnetic flux is changing due to the motion of the magnet. So here, the moving magnet generates electric field. That electric field is responsible for force acting on those electrons. Now, the legend says that Arne Ampere, who was a very prominent physicist at the time, lots of laws, he also was looking for a connection between magnetic field and electric field. And he used a galvanometer, a coil, and a magnet. But he was kind of afraid that a magnet, when it is close to a galvanometer, would affect. So he had a coil in one room and a galvanometer in another room. So and that's what he did. Nothing. Okay. Nothing. So he missed it. The tale says Faraday had a helper, a guy who was looking at the galvanometer like you now. So I don't have to. I move the magnet in, and something is happening. I move the magnet out, something is happening. So sometimes in physics, in science in general, little things make you famous or not. Well, Ampere didn't really care because he was famous already. Well, this is, again, the summary. The Faraday's law, when the flux changes, well, that's for single loop. The flux changes, it induces everything, including induced magnetic field. Now, we have to make a transition from just a general idea to certain calculations. We have to rely on our experience from PY105. If we look at this equation, that's velocity. Yeah. Symbol is different, but still. So everything we know about velocity can be used now. For example, we know that when an object travels and velocity changes, or position changes, velocity is equal to the slope, to the graph of position as a function of time. So we can immediately make a similar conclusion here. We still don't know, should we use a plus or a minus? But at least we know how to calculate the instantaneous magnitude of induced EMF. We just have to look at the slope of this graph. Now, every time when we use these words left, right, up, down, clockwise, counterclockwise, we assume a certain observer is looking at the system. But the laws of nature cannot depend on the, well, first of all, they just can't depend on the absence of the presence of intelligent species at all. We just write those laws for us, but they should exist independently. So, if you want to write a law which relates all those directions, we have to relate them independently from an observer. And I know that sometimes when I forget to control the way I talk, you may have no idea what I'm talking about. So that's why the next statement, because it's very important, I also put in writing. This is how we defined those two directions independently from any observer. It looks like it does, but it's not, because it says any direction. You can set the area vector in any direction. Yeah. And then you can use the magic, and you can figure out the direction of the induced magnetic field. And of course, because those are directions, we only have two options. They might be parallel to each other or opposite. And if they are parallel, in that case, we assign a positive value for electric current. And electric current is related to EMF by Ohm's law. Positive current means positive EMF. But if those two directions, area vector and induced EMF, are opposite, we assign a negative number. And it turns out, when we say we assign, the result doesn't depend on who does that or of any existence, which we will prove very soon. So I have exactly the same statement, but now using symbolic representation. Why don't we use verbal statements in physics? Because they take too much time. So that's why people have invented mathematics, symbolic representation. Only two options. When induced magnetic field and the area vector are parallel, induced electric current and automatically induced EMF is a positive, otherwise is negative. And that is my personal gift to you. You will not find this rule in any current textbook. Try. Question? Oh, that's supposed to be question number 5 now. I caught it. So whoever answered question number 5, now just do nothing. You had your chance. So, what do you say? And this is another example of a scientific thinking. This is where thinking is required. You have to apply a procedure which has been described before to a specific situation. The general procedure, specific situation. What do you say? What do you say? You moved, so don't move next time. What do you say? What's your choice? What two directions do we have to know in order to make an assignment, to make a conclusion? We need to know the area vector and induced magnetic field. Do you know the area vector? No. So not enough information. You have to make a statement and then follow it. That's it. That's how it works. So let's make a statement. Let's just see how it works. And of course, we have only two options. We can point the area vector out of the screen or into the screen, and it should not make a difference. That's the goal. If it makes a difference, it means it depends on the presence of the observer and how an observer is looking at it. So, out. Well, you stay. The area vector is out. Well, now based on all previous experience, we can say that here at the certain instant at t equals 1, t1 equals, I don't know, what is it, t1 some, whatever, could have been even equal to 0. Let's say t1 equals 0. That's when we start the stopwatch, doesn't matter. At this instant, the magnetic flux of the external magnetic field represented by these symbols. It's a number, so we have to choose between positive, 0, or negative. So this flux, area, magnetic field strength, well, number 1, times cosine of the angle between magnetic field and area vector. This is how sometimes people write it down. So positive, 0, or negative. What do you say? What do you think? What do you think? Area vector points out of the screen, magnetic field points out of the screen. What does it make? Out of the screen. They both point out of the screen. So there is no angle between those, or it's small angle. So it makes the flux positive. Now, again, in our experiment, we make the loop closer to magnetic field. That's why we have stronger magnetic field, larger flux inside. So at next instant, I don't know, 1 second, wherever it is, doesn't really matter. The flux A times B2 times cosine of the angle between, still positive. The area vector, of course, remains out. But now you want to compare two numbers, flux number 2 versus flux number 1. What do you say? Again, two numbers, which means we only have 3 options: greater, equal, less. If the area doesn't change, if the angle doesn't change, that means we should look at the magnetic field strength. And more magnetic field lines, stronger field, larger flux. So the flux number 2 should be stronger than the flux number 1. So the change, which is final value minus initial value, again is a number. As any number, it can be positive, well, 0, or negative. In this situation, what is it? What do you think? What do you think? What do you think? Positive? Yeah, we're subtracting two numbers. A smaller number from a larger number. So positive. Now we should look at the induced magnetic field. We already know it's into the screen. But we set area vector out according to our rule. What should we choose? The first situation or the second? The second, opposite to each other. So not this. The electric current is supposed to be set to be negative. Hence, so out of these two symbols, if we want to relate the value of induced EMF, which is negative, and the value of delta F, or delta phi, which is positive, what sign should we choose? If we write it like this, delta phi or delta t, we would have to say that some negative number, like negative 5, should be equal to some positive number, like, I don't know, 5. That is wrong. So a plus doesn't work. So the result is to relate actual values of the induced EMF and the rate of change of flux, we should write a minus. But that's only one example. Of course, we have to check what's going to happen. We have to check the independence. Well, now it's going to be quicker. The area vector points into the screen. Now, the flux will be negative. What about the flux number 2? Even like more negative. So if flux number 1, like say -5, the flux number 2 should be like -10, because the magnitude is larger, but it still remains negative. So if I want to relate these numbers now, 1 and 2, what symbol should I use? What is greater, -5 or -10? -5, that's mathematics. So -5 now is greater. So if I want to calculate the difference now, which is always final minus initial, which is kind of like -10 minus -5, what's going to be the result? Negative. But now, the same induced magnetic field points parallel to the area vector. So now we should follow the rule. And now the induced electric current should be positive, which makes induced EMF positive. So again, to relate the actual value of EMF and the rate of change of flux, we should use a minus. So it doesn't matter how we look at it. Of course, we can keep trying all other possible situations, and no matter what we do, no matter how we check it, we always get the same law. And this is the actual Faraday's law. He was able to figure it out, of course. It doesn't relate just magnitudes, it relates actual values. Well, this experience tells us that sometimes we don't really need to use area vector at all. So we don't have to. Only when we have to, we should use it. But if we have to use it because we have a flexibility, we always can choose the area vector in such a way so clockwise current will be negative and counterclockwise current will be positive. That's a summary. And now this law tells us what to do if we have many loops. We call it a coil or a solenoid. We just have to multiply by the number of loops. That's it. And this equation for the magnitudes we use when we need to solve an actual problem, calculate some number. But this relationship we use when we have to graph relationships. When we have to graph the flux or EMF. That's it. Well, this is the summary. A classical experiment, a magnet, a loop, a coil, a galvanometer, and let's practice. In this experiment, we are already told how to set the area vector. It is set for us, so we don't change it, we just use it. And for this choice of the area vector, we have to tell what? We have to say if the flux at this particular, in this particular experiment, when the magnet is falling through something like this. Now you're awake. Will be flux always positive, always negative, or changes from positivity to negativity, or first negative, then positive? Don't choose 5. Magnets and coils do exist. You know that. So And the answer, of course, again, is in the magnetic field lines. So I'm going to give you a minute to draw a picture which represents, well, 3 minutes, okay? To draw a picture which represents 3 locations. That's the first location. The second location, when the magnet is practically inside the coil. That's location number 2. And you should compose the picture relatively small because you will have to take a photograph of it and send it to me. I promised eventually this day would come. It just did. So, and now the coil and the magnet is traveling away from a coil. Normally, we also, to demonstrate what's happening, add a vector for velocity. Velocity, it's still falling down because we let it go, and magnetic and gravitational pull makes it move vertically down through a coil, which actually also can be demonstrated. All I need is this. It's going to be not as loud, but still. And when the magnet was traveling through, you saw the induced current. And to analyze the situation, to figure out how EMF changes in time, how electric current changes in time, we need to do this type of analysis. So now you should draw magnetic field lines, and then you should make a statement if the flux is positive, 0, negative, positive, 0, negative, positive, 0, negative. Again, this is a Greek letter phi, but people call it F. You can call it any way you like. Pu, P. And then you have to take a picture and email it to me. And I'll be back. You can discuss. So I think 2 more minutes should be sufficient. Well, it is time for me to check my email. It is time to send in emails. I have no emails yet. Except Washington Post. We knew who Trump was. Well, so why did you vote? So, first of all, of course, this question is just a review of the first slide from today, because it begins from magnetic field lines of a permanent magnet. And to review, if we have a magnet, this is the North Pole, this is the South Pole. Magnetic field lines are represented by loops, like this, like this. So, well, not all magnetic field lines travel through the coil, of course, only long ones. And here, magnetic field vector and area vector are opposites, so flux will be negative. Now here, we have magnetic field lines which also are inside the magnet. And the strongest magnetic field is actually inside the magnet. Or a solenoid. If you remember, we had an experiment with a solenoid. So magnetic field lines look like this. And in this situation, still magnetic flux is negative. But, of course, when magnet is far away from the coil, magnetic flux should have a relatively small magnitude, close to zero. And then, when it's getting closer and closer, magnetic flux is stronger and stronger. So, but it still remains negative. But then, when it moves away from the coil, well, magnetic field lines still are loops. And at the location of the coil, they still point opposite. But now we have again very, very low flux. So something like this should be happening. So it remains negative all the time for this particular choice of the area vector and the orientation of the magnet. And that's the graph. And of course, next question is, how would we sketch the graph for EMF? Well, for that we need to use this relationship between the induced EMF and the slope. Well, at first, just for the matter of practicing, I recommend to sketch the graph for the slope itself. So here, the graph for the flux is practically horizontal, so practically there is no slope, zero. What is happening to this slope? Well, it's negative slope, not zero anymore. And it increases in magnitude. But eventually, we can see it should go back to 0 because it again becomes horizontal. So between 0 and 0, we should have a point where the slope reaches maximum magnitude. So the shape of this should look like this, something. What next? Well, now the slope is not 0 anymore, but positive, and then more positive, and more positive, but eventually becomes less and less inclined and eventually goes back to 0. So something like this. But that's not the EMF. What is the difference between the EMF and this graph? EMF is equal to -1 times the slope. So if you want to sketch the graph for the EMF as a function of time, you just have to take this graph and flip it. That's what this means, multiplying by -1. So flipping something like this. Now, for the first part, EMF is positive. For the second part, EMF is negative, or electric current, positive or negative. And first part, yeah, it is when the magnet is approaching the loop of the coil and eventually reaches the middle point. And the second part, when the magnet now is moving out and eventually traveling infinitely far away. And again, this part, analyzing slope, is what we know from PY105 because we've done it before, the graphs. Now, an example of a standard problem. A loop has certain dimensions, certain resistance, and magnetic field increases steadily, which means with a constant rate, from 0 to 1 in 10 seconds. That's it. It's not a circular loop. For the circular loop, we would need a radius. This is a rectangular loop, which, well, doesn't really matter. Yeah. So first, how many turns does it have? Well, single loop, n equals 1. And the average EMF is equal to the rate of change of the flux. How does the flux change? Well, the flux is equal to B times A times cosine of theta. And if I want to calculate the magnitude, this will be just B times A. I know that no matter how I choose the area vector, the angle between B and A will be 0 or 180. So cosine will be 1 or -1, and magnitude of that is 1. So how does it change? Well, because magnetic field initially is 0, and then it is equal to 1. That's how the flux also changes in 10 seconds. So the flux initial equals 0. The flux final equals 1 Tesla times area, which is 1 times a half. That gives a half over that unit we call Weber, Weber, Weber. And that happens over 10 seconds. So if you want to calculate the induced EMF, 0.5 over 10, 0.05 volts. And if I want to calculate the induced current, 0.05 over 0.1, 0.5 amps. That's it. So with the numbers, if we use that equation, we just have to carry out a straightforward calculation. Now, do we know how magnetic field points into the page? Okay. How do we know? We have eyes and we can read. So the magnetic field, initially actually there is no magnetic field at all. It starts from 0. But if we wait 1 or 2 or 3 seconds, we're getting some magnetic field lines inside that loop, enclosed. Yeah? And how do they point? Into the page. Well, now we have to choose our point of view, and our point of view naturally is, well, down on the page. So we would see magnetic field lines directed away from us into the page. So now we can choose which picture would tell us the answer. Well, definitely not number 4 and not number 3. So we have to choose between number 1 and number 2. In the picture number 2, the flux decreases in magnitude. We have a lot of magnetic field and then less. In our situation, the flux increases in magnitude. So again, that's wrong. And the correct picture tells us that the induced magnetic field should point out of the screen, and the induced electric current, from our point of view, should be counterclockwise. That's it. So this is the summary of the Faraday's law, but now we add in one more law. Technically, we don't have to use it. Yes?
For the problem we just solved, if we wanted to, we could just choose the area vector, reason from that, right?
Yes? But this is an example of a situation when we don't have to and we don't need to use any choice of the area vector. We didn't have to.
But then would we have to know the...
No. If you choose the area vector, again, you have to choose it from a certain point of view. And let's say if you choose it right, everything will be consistent. If you choose it wrong, you will change your choice. It's a situation similar to, for example, collisions. When we have two cars collided, we don't know the answer. So we choose that after the collision, they all travel to the right, and then we calculate. And if it's negative, we change, our assumption to the right one. It's a similar idea. You have to try it. You want it, you do it. Because we don't have to. We don't.
But how would I know if I didn't have this picture?
You would have to use this, what I'm going to talk about now. So that's exactly what I wanted to say. We have two options. The option number 1, memorizing all 4 situations. But of course, since it's a science, there is a general rule which will automatically give away the final answer. That rule has a name, the Lenz's law. That's what it says. Changing magnetic flux induces a response that tends to oppose the change. That doesn't require understanding. That requires memorizing and practicing. So the meaning of this is simple. When magnetic flux changes, the induced magnetic field might help increase, speed up that change, or might slow it down, kind of damp it, decrease that change. And to do that, the induced magnetic field might either have the same direction as the external magnetic field, and that will help the change. Yeah? That will help the external flux, or like in this example, induced magnetic field has direction opposite to the external, so it tries to kind of keep it down. So what we need to, well, this is the same slide, but letters are larger. What we need is to practice. So this is a summary for all laws together: Faraday's law and Lenz's law. And this is, we start thinking about how to use this. First of all, what kind of a change might happen when flux changes, or anything? That variable which changes only can increase in magnitude or decrease. So only two options for the change. What to oppose means to slow that change down. So if it increases, we want to slow it down. If it decreases, we want to slow it down. But in order to slow down increase, we have to point the induced magnetic field opposite to the external. In order to slow down the decrease, we have to point the induced magnetic field in the same direction. So just an example. Magnetic flux increases. Again, we can choose our point of view straight down, and we can out, just for the sake of the change, we point the external magnetic field out of the page. And increase means over a certain time interval, we have more magnetic field lines enclosed in the loop. So that's what increase means. Now, to slow down that change, the induced magnetic field, according to the law, should point opposite. Why? Because that's how vectors should be added. If we have a few vectors and then we have more, to slow down that change, we should add vectors which point opposite. Now, what does a decrease mean? Okay. Here, I'm going to start from a situation when we have a lot of magnetic field lines, and then the number of magnetic field lines decreases, flux drops. To slow that change down, the induced magnetic field now should be parallel to the external, because what's happening? We have a lot of magnetic field lines, and then the number drops. To slow it down, we should add magnetic field lines in the same direction. That's what slow down means. So instead of memorizing 4 pictures, you can now use this rule. To use this rule, the method has been developed which is based on drawing 3 pictures. The picture number 1 has a name before, meaning before change had happened, after, and the last picture has a name to oppose, but that's just a slang, a term. It represents the direction of the induced magnetic field. That's the description of the steps. Draw a picture which depicts the initial state of the flux inside the loop. Next, draw the picture which demonstrates induced field opposing the change. And then, in the end, you can make a conclusion about the direction of electric current. So all we have to do is practice. A loop, we can draw any shape: circle, square, triangle. Well, circle is fastest. in a magnetic field pointed into the page. That's the picture which demonstrates the initial situation, which has a name, before something has happened. All right. Now we have to draw a picture which demonstrates the presence of magnetic field inside the same loop after a certain instant. So it's the same loop, a magnetic field points in the same direction, but now we have to make a choice. Do we draw the same number of lines, smaller number of lines, or a larger? There is a specific word, one single word, which tells us what to do. What word is that? An increase. So we have to draw some extra crosses, each represent magnetic field line traveling into the page. Like this. Now we have to draw the picture which says to oppose, that word, to oppose. What should it oppose? It should oppose the change happening to the external magnetic field. So what is the name of that change? An increase. To slow it down, what should we do? We should make a choice between directing induced magnetic field as the external or opposite. If we want to slow down the increase, we have to point the induced magnetic field opposite to the external. Opposite. Well, and now we have to draw that picture. What is opposite to into the screen? Out of the screen. And this is our picture. The third picture. This picture doesn't show electric current, but we know that the direction of electric current is related to the direction of induced magnetic field. So we have to choose between clockwise or counterclockwise. The rule says counterclockwise. That's it. This logic works every time when magnetic field enclosed inside the loop changes. You will practice, you have similar situations to analyze, problems to solve. And we will practice. So, this is, yes?
And when we know the current direction, like counterclockwise and clockwise, is it same as like when it's like torque and like counterclockwise is always negative, and like is there a connection like that? Or
It depends on the question. In this question, all we have to do is make a final statement about the direction. If you want to make it positive or negative, if you have to add an additional statement about, well, normally now we know, now when we know how induced magnetic field points, we can set area vector in that direction. We need area vector when we have to draw a graph. In that case, because a graph has numbers, positive or negative, we should make a statement about positive or negative values. In this situation, no one asks us if it's positive or negative, so we don't care. So this is the description of the whole procedure. Questions we should ask ourselves and answer one by one. What are the direction of the external magnetic field, what is happening to it, how should we slow it down, and how eventually the induced electric current points. And now, of course, well, this is the slide we saw before. I just want to mention that we also can read it backwards. Sometimes we may know already how the induced magnetic field points, and we should make a statement how it's been done. In that case, we just have to read those situations backwards. For example, if we know induced magnetic field points, well, how do we call it? We would say up. But for a person looking down, that would be out of the page. For the person looking from below, that would be into the page. So all those names are relative. And how can it happen? Well, we have two options. To make induced magnetic field up, the external magnetic field should be up and decreasing, or the external magnetic field should be down and increasing. That's it. Well, this is not a question to you. This is just another example. This example involves, it's very important, so-called a proper galvanometer. What is a proper galvanometer? It is a galvanometer for which we know how it will be deflected if we attach a battery to it. So this battery, as any battery, has two electrodes, positive and negative. And for a proper, let's see if this should be proper. For the proper galvanometer, if a positive electrode is attached to a plus, it should deflect it to the right, which means electric current travels into the positive electrode of the galvanometer. But now we can use this backwards. If we see that it deflected to the right, that means electric current travels into the positive. For example, if I use this coil now, now I know this is a proper galvanometer, I can tell you the direction of electric current. For example, because it deflects to the right, when I was moving magnet into the coil, electric current should have been traveling into this electrode. And now, if I move it out, the deflection to the left tells me that now electric current travels like this, in opposite direction. And in this problem, we use a proper galvanometer. So how do we use the pictorial method before after to oppose? Well, first we have to start from magnetic field inside the loop. The source of the magnetic field is this wire. So we can use actually this way. The right-hand rule, electric current travels down here. Magnetic field points into the screen. Here, magnetic field also points into the screen. So magnetic field inside this loop points into the screen. That's what we know. So our first picture shows magnetic field directed into the screen. Now, what is happening to magnetic field? Well, the flux is proportional to this product. Magnetic field strength is proportional to current. When electric current increases, that makes magnetic field stronger. That makes magnetic flux larger. So the second picture should have more magnetic field lines. Now we use that rule to slow down the change. The induced magnetic field should, and now we should say, be opposite. That the induced magnetic field, it should be opposite to the external. Now we can again say, okay, if the induced magnetic field points out of the screen, the induced electric current should travel like this. And if I imagine myself looking down, I can say these words counterclockwise. Now I'm going back to my picture. Okay, this is my galvanometer. It's plus, this is minus. So this is my loop, and electric current travels like this. So it travels. It goes into the positive electrode. That means the galvanometer should be deflected to the right. That's how it works. Questions? All right, so we saw this slide. Now, just again, for the sake of the practice, let's draw pictures before, after to oppose. And we need to set the point of view, and normally it is from above. So we should imagine a person looking down at those magnetic field lines. So at the location of the loop or a coil, for that person, magnetic field lines point out of the screen. And we know that this experiment has two different regimes, approaching and then moving away. So this is for approaching. For moving away, pictures should be slightly different. You have a question? Yes? Away from that person. This is not an A. This is supposed to be an I. What's the saying? The beauty is in the eye of the observer. And in physics, the direction is in the eye of the observer. So a person looking down, those lines travel away from that person. We have to choose point of view if we want to draw those pictures. But we know in the end, the point of view will not matter. Description will be different. The phenomenon will not. Now, when the magnet is approaching, it means flux increases, more and more and more and more lines. And again, we know in that case, the induced magnetic field should be opposite, and that will make electric current in that direction, which is counterclockwise from the point of view of the observer looking down. Now, we can make it positive or negative, and naturally, of course, if we choose the area vector in the direction of induced magnetic field, we make it positive. So this is current, and that's the first part of it. And moving away, what's changing? We got a lot of flux, then less flux, and now induced magnetic field, to oppose the change happening to the external field, should actually point in the same direction. That's be induced. That makes electric current clockwise. So direction and positivity, negativity, well, the universe doesn't have numbers. But we need them to communicate with each other, to describe what we see. All right, so I just did that. And graphs. Here is a case which tells us that technically there isn't much difference between using Faraday's law or motional EMF equation. A loop is traveling through a region with magnetic field. Well, first, there is no magnetic field, so the flux is zero, but more importantly, it remains to be zero, constant flux. Nothing is being induced. when the loop is entering the magnetic field. So more and more flux, electric current supposed to be induced. Because of what? Because of the Faraday's law. But also, we could look at this loop as made of 4 rods. Yeah. Number 1, number 2, number 3, number 4. The rod number 1 is outside of magnetic field. Nothing can be induced in it. The rod number 2 is parallel to velocity. That's how velocity points. The rod number 3 is parallel to velocity. Well, anti-parallel. Parallel. Okay. So there's only one side of this loop which starts acting like a battery. The rod number 4. How does it act? Well, we have to use again the right-hand rule. Magnetic field velocity, positive charges would move up. So this rod starts acting like a battery with, well, something like this. And in this situation, electric current induced would travel outside of the battery, away from plus toward minus, like this. That would have been, and we can repeat the same reasoning again and again. When the loop is completely in the region and travels, to keep traveling to the right, the magnetic field is not zero, but magnetic flux does not change anymore. If there is no change, delta phi is 0, there is no EMF induced. In terms of batteries, how would it make it work? In terms of batteries, we would say, well, there is a battery here and battery there, and then induced electric current in opposite direction, which cancel each other out. And then we can repeat the same reasoning again and again and again. So Faraday's law, motional EMF, doesn't matter. Of course, same physics. And one more blast from the past. So we know this relationship in general. This is the graph, and the slope of this graph represents a different graph. Could have been position and velocity, but could have been flux and EMF. But these graphs are also related backwards. If I know this area will be equal to the change in the original variable. Well, we know that these graphs for the flux and EMF are related. And we know that the relationship Windows lost my symbols. We know that relationship can be read backwards. So this is how we can relate area, initial flux, and final flux. And that's what you're going to be doing today and tomorrow in the lab. Thank you. That clock is late. It's 5 minutes late.